Okay, in this podcast we're going to take a look at what effect temperature has on rate, and in that discussion we're going to talk about activation energy and ways to lower activation energy, specifically using catalysts. Okay, as you would imagine, if you increase the temperature, you're going to increase the reaction rate. Okay, so here we have a little plot that has K in temperature, and K is dependent on temperature. So in a chemical reaction, bonds are broken and new bonds are formed. Now it's a little bit of a misconception, but whenever bonds are broken, energy is required, and whenever bonds are formed, energy is released. It gets confusing because people hear others talk about chemicals storing energy, and that when you break those bonds you release that energy. And in fact, that's not really the way it works. When you break those bonds, it requires energy to do so. If other bonds form, that will reduce the energy. Okay, so let's get that clear. Alright, molecules can only react if they collide. Okay, only way it will happen. They can't just see each other, they actually physically collide. So before collision, you have two species, atom, molecule. They collide, and in the process of colliding, they actually form this, what you might call an intermediate. And after they collide, they break apart into their two new products. Okay. So this whole area of what's going on in here is what we're going to be addressing with this podcast. So the other thing we saw in that diagram is there's some minimum amount of energy that's required to get that reaction started, and we call that energy activation energy, and we give it the symbol E for energy, sub A for activation. Okay, just like a golfer golfing, you need some energy to get that ball over the hump, and then it can move on to the tee. Okay, so a reaction can't start unless there's sufficient energy to get it started. So this is we're going to draw a typical diagram, but what we call a potential energy diagram. This would be potential energy on this side. This is reaction progress or time on the x-axis. Okay, so here we are looking at a reaction where we start with reactants. They require some amount of activation energy to get them going, and then we have products at the end. So what would this be, an exothermic or an endothermic reaction? Well, as you can see, the products have lower energy than the reactants, which means the energy was lost, so this is an exothermic process. And as we talked about in our thermo section, the difference between where the reactants start and the products come out is our change in enthalpy, right? And then this additional piece is the activation energy. Okay, but we don't count that activation energy in the change in enthalpy. So what happens here is that point in between where we have reactants and products, where the reactants have collided together, come together, and start the rearranging process before the products come out. Okay, and we call that the activated complex. Okay, so this is where the activated complex is, and we call this also sometimes the transition state. So let's say we have a reactant, and a reactant A and a reactant B, and they come together and collide, and as they do that, they start to rearrange what's going on with electrons and sharing, and so we call this the activated complex. Now out of that we end up with two products, both product C. So if you could imagine, here's a more complex reactant. We start with this reactant. There's some rearranging that occurs. Okay, we reach this activated complex and then end up at a new product down here. Okay, So it's this rearranging of the molecule as things go that causes this activated complex or the transition state. Okay? So we call this high point the transition state. The species present at the transition state is called the activated complex. And the energy barrier between the reactants and the activated complex is called the activation energy barrier. That's the barrier or the hump that the golfer needed to get over, right? It's the energy barrier we need to overcome in order to cause the reaction to start. So what happens here is we look at the effect of a catalyst. Okay, so what's happening is, this is called the Maxwell-Boltzmann distribution. If you take a sample of some molecule or atom or solution, what you'll find is that they don't all have the same speed. That there'll be some distribution of speed that has some with very low energy and some with higher energy, but most of them are this average energy, right? And as you increase the temperature, what you are doing is you are causing this skewing in this Maxwell-Boltzmann distribution, right? And if you can imagine, this dotted line indicates the minimum energy for a reaction. So at any temperature we have this wide distribution. As the temperature increases, the curve flattens and broadens. So at a higher temperature there's a larger percentage of molecules that have enough energy. Here, when it was the lower temperature, we had just this blue area which represents the number of particles that have enough energy. But as we raise the temperature and flatten this curve, now we have this whole area, blue and red together, which represents the number of particles that have enough energy, causing you to come over the curve. So we can define the fraction of the molecules, and don't worry about this equation, but it's related to the activation energy, R, which is the gas constant, and T, which is the Kelvin temperature. Okay? So as we get enough molecules higher in energy, the reaction rate increases. Okay? So without some catalyst, it requires this much energy. If we have a catalyst, it's going to require some lower amount of energy. So what a catalyst does is it lowers the amount of activation energy. And the other interesting thing about a catalyst is you add it at the start of the reaction, at the end of the reaction it's still there, unaltered. Now Arrhenius came up with this equation that so if I have an exothermic reaction, the energy of activation is here, leading me to my products, which would be at lower energy. Okay, so the activation energy is the minimum amount of energy. It doesn't matter whether it's an exothermic or an endothermic process, there's still some amount of energy. So here where I'm endothermic, I've got to put energy in. It's this whole distance is my activation energy, because I got to go from where I am to the activated complex. Okay? And if you remember, this it's just this distance here that's going to be my delta H. It would be this distance here that would be my delta H over this side. Okay. So let's see if we can answer these questions. So here I have 3 graphs, potential energy diagrams, showing what's required for activation energy. So rank their reaction from slowest to fastest, assuming that they have nearly the same frequency factors. Okay. So let's take a look. So what effect is this activation energy going to have on my rate? It's going to have a pretty big one, right? So what I want to do is look at what it's going to take for me to get over the hump. Here it's going to take 15 kilojoules. Here it's going to take 25 kilojoules. And here it's going to take 20. So this should be the fastest, and this should be the slowest. Let's see. So the lower the activation energy, the faster the reaction. Hence the order is 2 is the slowest, 3 is the second slowest, and 1 is the fastest. Okay. What if we looked at the reverse reaction? Okay, let's rank those. So let's see, I have to go from here to here. That's going to take 25 here. Here I've got to go from down here. This would be my reactants. This would be my product. It's going to take 40 kilojoules. And here, my reactants are here, and I need to get up to here. That's only going to be 20. Okay. So this is going to take the most energy. It's going to be the slowest. This would take the second most, 25, and this would take the least. This is not sure how they, which is 20, if it's this or this, but it's probably 15 is what I'm looking at here. Okay. Okay, because the energy of activation, 2 is going to be the slowest, and 3 will be the fastest. Okay, so that makes sense. Okay, we're going to stop there.